Day 8 deals with concavity, the second derivative, and the second derivative test. Concavity is determined by the rate of change of the first derivative. So if your first derivative is increasing, you have a concave upward shape, and that's this left picture. The first derivative, or the slope of the tangent line, is negative here, but then the next place it's a little bit positive, and the next place it's even more positive. So the first derivative is increasing, which produces a shape that looks like a bowl or a cup. If the rate of change of your first derivative is decreasing, then you'll have concave down. That's what's happening in this plot. The first derivative here is positive. At the next location, it's slightly negative, and at the next location, it's even more negative. So the rate of change of the first derivative, or the first derivative, is decreasing, which produces a concave down graph, which looks a little bit like an umbrella. If the first derivative is increasing, then the second derivative will be greater than 0 or positive. And that's how you determine if something is concave up. If the second derivative is negative, then that means your first derivative is decreasing, which produces a concave down graph. If your plot ever changes from concave up to concave down or vice versa, you're going to have a change in sign in your second derivative. Concave up, the second derivative is positive. Concave down, the second derivative is negative. So at some point, the second derivative has to either equal 0 or not exist. Notice that the first derivative doesn't have to equal 0. The slope of the tangent line here is not 0. So when you switch from concavity in one direction to concavity in the other direction, we have what's called a point of inflection. So there is a point C where there's a change in concavity, and that point has to occur at either second derivative equal to 0 or second derivative does not exist. But the converse statement is not necessarily true. Just because you have second derivative equal to 0 or second derivative not existing doesn't necessarily mean that you have a point of inflection. So as a second example, we have concave down, which means the second derivative is negative. Concave up, which means the second derivative is positive. Between there is a point of inflection because there's a change in concavity, and in this case, the first derivative happens to equal 0. The second derivative here at this point C would either be equal to 0 or not existing. And then the final example, concave up, second derivative is positive. Concave down, second derivative is negative. Point of inflection right there, but the first derivative does not exist. So again, at this point here, either the second derivative is 0 or the second derivative doesn't exist. The first derivative here, we can see, does not exist. One of the results of the second derivative is the second derivative test, which helps us determine if we have a minimum or maximum using both the first derivative and the second derivative. So if the first derivative equals 0, we know that we have a horizontal tangent, and if the second derivative is greater than 0, so at that horizontal tangent we have a concave up situation. So the picture for that would be second derivative equal to 0 and concave up, which means we have a minimum at that point there. The other case that could happen is if your first derivative is equal to 0 and the second derivative is negative, let's highlight that, and the second derivative is negative, then you're going to have a maximum because your picture would look like this. Second derivative is negative, which means concave down. First derivative is 0, which means you have a horizontal tangent. Therefore, you have a maximum at that point there. That's supposed to say maximum. Okay? If the first derivative is equal to 0 and the second derivative equals to 0, then the second derivative test fails, and you'd have to do something else like going back to the first derivative test. So if it's easy to take a second derivative, and if you can determine very quickly whether that second derivative is positive or negative, then wherever the first derivative is 0, you can use the sign of the second derivative to determine whether they have a minimum or maximum, and draw a little diagram to help you figure that out. Okay, your job in this one is to take this function, find the points of inflection, discuss concavity, find L relative extreme, and use the second derivative test if applicable, and then make sketches of the function, the first derivative, and the second derivative. So I gave you a bit of a head start. The first derivative using the product rule is this. In order to work with it a little bit better form, you take and factor out the common terms, which is x minus 1 squared. Combine the like terms on the inside of here, and now you have the first derivative with x minus 1 squared times 4x minus 7, which produces critical points of 1 and 7/4. In order to find the points of inflection, you're going to need to do a similar process with the second derivative. So take the second derivative, find common factor terms, factor it out, and then set it equal to 0 and solve for possible points of inflection. Pause the video and work out that second derivative part. Okay, second derivative is there. Using, again, the product rule. Factor out 2 and x minus 1. The remaining stuff inside the parentheses boils down to 6x minus 9. Setting equal to 0 and solving gives you possible points of inflection at 1 and 3/2. So the next step is underneath your plot making a table for what happens in different intervals for the first derivative and the second derivative. For example, take your critical points of 1 and 7/4, test numbers on either side of it and determine whether or not the first derivative is positive or negative, and then take your possible points of inflection of 1 and 3/2, test points on either side of it and figure out if the second derivative is positive or negative. Once you label your positive or negatives for the first and second derivative, you'll know whether your function is increasing or decreasing and whether your function is concave up or concave down. Fill out that table, pause the video, fill out the table, and then look at the answers. Here's the table. The first derivative is negative until you hit the critical point of 1. It's negative between 1 and 7/4, and then the first derivative is positive above 7/4. The second derivative is positive until you hit 1, negative between 1 and 1.5, and then positive past that. Now take that information and the roots and try and plot the function first with decreasing, decreasing, increasing, and then concave up, concave down, concave up. Make a sketch for f. Here are the final answers. F is decreasing, has a root at 1, decreasing, increasing, right past the critical value of 7/4, has another root at 2, and then continues up forever. The shape is concave up until you hit the root of 1, then it switches to concave down, so 1 is also a point of inflection. Concave up here, concave down here. There's another point of inflection right here at 1.5, which is kind of hard to see, but it switches from concave down back to concave up and remains concave up the entire way. So to sketch f prime and f double prime, f prime is just the function that has a root at 1 and a root at 7/4. So if the original function was 4th degree, f prime is going to be 3rd degree. There's a root here and a root here. You know that it's negative, has a root, remains negative, has a root, and turns positive. And then the same kind of a thought process for the second derivative. You have roots at 1 and 3/2. 1 and 3/2 gets a green dot for the second derivative, and you know that the second derivative is positive, negative, positive, positive, negative, positive. You can use Desmos to plot the true shape of these three graphs if you want to. So in the last example, you're given a bunch of characteristics and you're asked to sketch the graph. So these two things are x-intercepts or roots, information about the first derivative in these 3 spots, and information about the second derivative in these 3 spots. Some hints. Go ahead and try and fill out your table. We'll check the table and then we'll plot the graph. Okay, hopefully you filled out the table. First derivative, the function is decreasing and then increasing because the first derivative is negative when x is less than 1. First derivative is positive when x is greater than 1. And the first derivative at 1 is 0. So there's a horizontal tangent at 1. We have roots at 0 and 2, so I can put those down. Root at 0 and 2. We know by the first derivative test that we'll have a minimum at x equals 1, and then it's concave up everywhere. So what does a plot look like that's decreasing, has a minimum, and is increasing and always concave up? Looks like a parabola. We don't know where the minimum point is. Haven't learned that yet. But as long as your function is decreasing, minimum at x equals 1, and then increasing concave up, you have the correct graph. All right, that's it for day 8.